Okay, great. Good. So so from the previous two classes, we've been talking about we've been going into black holes, and so just a reminder of what we've been doing. So we know that once we have the solution, for example, previously we have the short shell solution. We know that there's coordinate singularities. There's singularities that are not really there, but just because of course coordinate system. So that actually means two things. One is, of course, we already know that it's not a true singularity. It's really just an artifact of the coordinate system. But it also tells you that whatever coordinate that you started with, that coordinate is no longer valid after you go past the singularity. So you need to find a new coordinate system in order for you to allow you to go across that singularity. So just for example, in the short shell case, we have the horizon at RS, and we find that there's a singularity there. So of course, we know that it's not a true singularity, it's just a coordinate system singularity. But that also tells you that starting from the radial coordinates that we have, in order to talk about space-time going into the horizon, we need to find another coordinate system which is smooth as you go across the horizon, and therefore allows us to actually go into the horizon and discuss physics there. And so that was basically what all these coordinate transformation that we were doing was really meant for. It allows us to go from something from outside of the black hole or outside of the event horizon going inside. And in the process, we've developed our understanding about the causal structure, how the causal structure changes. So this is basically a notion of analytic continuation. So you have two coordinate systems that match on the outside. So for example, when we start from the radial coordinate and we went to the Eddington-Finkelstein coordinates, of course, these coordinates are the same on the outside, but only the Eddington-Finkelstein coordinate allows you to go into the horizon. And so this is a notion of analytic continuation. So that's basically what we've been doing most of the time, what we've been doing. So today what we're going to do is we're going to do the same with Raiser-Nordstrom black holes and so as well as for rotating black hole. So since we already have experience in the short shell case, so many of this will be very similar to what you've already seen in the short shell case. And so there'll only be some slight differences, but the slight differences is extremely important because that means a drastic different structure for different causal structure. So let's begin. So first part, we're going to talk about Raiser-Nordstrom, so which we discussed, wait. Sorry, 1 second. Oh no. Let me see. So if I just charge you a little bit. Okay, let's see how long this can. I'll try to. Okay, I'll try to charge it in the middle. So right. So let's start with Raiser-Nordstrom, which is a charged black hole in the Einstein-Maxwell system that we talked about last time. So let's set our conventions for today. So once again, the black hole solution looks like this. So first of all, it's still that the time component is inverse of the radial component. And then so this is still a spherical symmetric black hole. And of course, the difference is that not only do you have metric, you also have the vector potential, which is associated with the Maxwell field. So the solution here for the Maxwell field is that it is given by this. So I'm going to assume that this thing carries both electric and magnetic charge. So what this means, of course, usually we don't have this piece in our vector potential. When you only have electric fields, you only have the time component piece. But when you have magnetic fields, you have this. You also have this extra piece here, and this extra piece here is associated with the fact that you have magnetic charge. So P will be my magnetic charge, Q will be my electric charge. So this is like if you have a magnetic charge, so this will be like a monopole black. If Q equals 0 and P is non-zero, this will be like a monopole black hole. And of course, once you have your vector field that takes this form, then of course, then you know that you have two non-vanishing field strength. So you have the time and the radial component equals r squared q. This is the electric field that you usually have. And then you're going to also have the magnetic field associated with it. So it's in the spherical coordinates or in the polar coordinates, it's in terms of theta phi, in the theta phi component. Okay. Now, of course, delta here, we've already talked about this before. Delta here is just 1 minus r naught. So this is the usual Schwarzschild piece. But then because of the fact that you're electromagnetically charged, therefore you have an extra piece, which is like this. Okay. And as we know that since this is a quadratic equation, we usually write it as 1 over r squared with r minus r plus and r minus r minus, which is that we have two roots here. Okay. So basically we have so basically the statement is that we have two roots. And so this is different than the Schwarzschild black hole. So once again, we can find, so let's find, so here we would like to talk about, so we're going to do exactly the same thing as Schwarzschild black hole. And that is that we know that because of this singularity here, if we draw it out, because this delta is appearing in the denominator in your radial component. So that means that when we talk about the black hole, like let's look at the metric as a function of r, we know that there's r plus and then there's r minus. Okay. And so that's the two roots of your delta, and therefore your coordinate is bad here and here. Right. So really what we have, even though we have the solution, but we have this Reiser-Norton solution, but this solution is really valid for coordinate system outside. We want to go inside here. So we want to find a redefinition of coordinates that allow us to go inside. Okay. And so we can do exactly the same thing. If you remember how we got so we're going to do the Eddington-Finkelstein coordinate. And remember that, how do we get the Eddington-Finkelstein coordinate? Remember that what happened is that, I mean, we can see it here. So let's consider null geodesic. If we just look at null geodesic again. If we look at null geodesic at fixed theta and phi, if we just fix the theta and phi coordinate, then, and here the null geodesic is just going to be 0 equals to dt square, go to minus delta dt square plus delta minus 1 dr square. So this tells us that dt dr is just going to be equal to 1 over delta, right? So that means your null coordinate, so once again, at r goes to infinity, so this is your delta. So as r goes to infinity, this is just becoming 1. This is just becoming 1. So this is the usual case where at infinity, this looks like the usual light cone. The null coordinates are the usual light cone. But as you go closer and closer to r plus, the first divergence, this light cone is closing up, right? So this light cone is closing up. So basically, you want to find a new coordinate system such that the light cone always maintain 45 degrees, right? That's what you want to do, and that's basically the Finkelstein, the Eddington-Finkelstein coordinate. And so to do this, so let's see. So basically, I mean, in a nutshell, right? So we want to solve the null geodesic. But we already know that the null geodesic takes the form of this minus plus delta minus squared dr squared. So basically, you just want to find something such that dr square over dr, just do a change of coordinate that equals dr tilde squared. I mean, that's in a nutshell what people are doing when they're doing the change. They're doing this change of coordinate. So you're actually trying to find a dr tilde as a function, your dr tilde as a function of r, such that this change of coordinate removes this delta minus 2. So in other words, what you want to do is you want to solve the following equation, right? You want to solve that r to the 4 r minus r plus square r minus square dr square is going to be equals to dr tilde square, or that dr tilde dr is going to be equal to r squared r minus r plus r minus r minus. Okay, so that's the whole notion of doing the Eddington-Finkelstein coordinate system. Okay, and just solving this, you can just directly check that this is indeed is a solution. You get that r tilde is basically just equal to r plus 1/2. Let me call this k plus long r minus r plus over r plus 2k minus long r minus over r minus, where k plus minus, can you guys see this? Can you guys see this k plus minus thing here? Is it too little? I mean, is it too in the bottom?
Yes, too oh.
Too low, okay.
Too low.
Okay, so where this k minus and k plus here, this is given by, so k plus minus, it's just some linear combinations of plus minus r minus plus over 2 times r plus minus. Square, sorry. Do you guys know what this means? This plus minus, it just means that if it's k plus, that it's going to be r plus minus r minus over r plus to the square. So if it's bottom k minus, you just choose the bottom label. Okay. Okay, so this is just some constant. It's not a function of r. It's just some constant. Okay. Great. So this is doing exactly the same thing as you did before. So this is just your usual Eddington-Finkelstein coordinate, and so therefore we can do exact. So all you have to do. So now we can successfully continue in here. So the story is exactly the same, and so we can do basically exactly the same thing, and we can talk about. So for example, we can talk about u equals to t plus r tilde, and v equals to t minus r tilde. So u will be the infalling coordinate frame. V will be the outgoing coordinate frame. Will be the outgoing. And your metric, so for example, your metric, you can write it in terms of the infalling frame, and it will just look the usual du. So this is exactly, so everything here is exactly like the short shell, except that what we mean by r is delta is now different. In short shell, this delta was 1 minus r s, if you remember. Now this is r 1 minus r minus r plus, and sorry, and r minus r minus. This is what delta means. But aside from that, the coordinate system looks the same. So we also have so in the infalling frame, it looks like this, and exactly the same thing we're going to get for the null geodesic. We're going to get for the infalling frame, we're going to get du dr. The null geodesic is you just set this to 0 because we're at fixed angular angle, and then we're just going to have these two terms, and therefore you have du dr is just going to be equal to 0 for infalling, and 2 over delta for outgoing, right? So is everything fine?
Is that R or R tilde?
This is R. Yeah, oh, sorry. I think that, oh, sorry. Yeah, this is R tilde, sorry. Right. Okay. So can anyone tell me why this is 0 again? Why is that 0? Why is m falling 0? Why is the m falling no geodesic 0?
Because U is constant.
Very good, because because in the infalling coordinate, remember that when we're doing infalling coordinate, we have U set to constant, right? That's the infalling one, right? So that thing is 0. Okay, so everything looks exactly the same. Just 1 second. Let me just check one thing that I have everything correct. Okay, so basically we're going to have exactly the same thing. And the infalling is going to be 0. So let's say we're going to have R plus and R minus. Okay. So let's see what happens. So the infalling is always going to be 0. So it's always going to be flat. So it's always going to be flat. Sorry. Yeah, my iPen just died. Just need some battery charging. Okay, let me charge my pen for 10 minutes. Sorry. Do you guys want to take a break for 10 minutes and then we continue? Because as you can see, I have no battery in my iPad. I think 10 minutes should be enough. Do you guys want to take a break for 10 minutes? Or we can, but I can't really write anything right now. Yeah, sorry. So let's just take a break for 10 minutes.
Okay.
We can chat about anything you like, or you guys can get some water or something. Sorry, I need to check. I forgot to charge my iPad.
Oh, okay.
Okay, so we'll regroup. So I'll stop recording here and we'll regroup in 10 minutes. Okay. Sorry, guys.